Thales was doing when he went to Egypt and told the farmers where their farms were after the Nile had flooded. And it did it every year. That's where geometry got started. And that's a long time ago, 600 BCE. Okay, are we back on screen? So, what I'd like to do is just real quickly go through those numbers just to make clear. Now, those parameters vary like heck as a function of velocity. And sometimes they cross and you get weird symmetries when that happens. I haven't explored all of that. That's to be done. In any case, the idea here is that we have the baseball diamond here, which is the per space time, and then we have real space and time up here. So what we're doing now is filling in that table in a couple of steps. And basically this 5/4, 1 1/4, right here, that's the coordinate of the phase vector, okay? And it has the cosine on the vertical part. That's the hyperbolic cosine, remember. And there's a hyperbola waiting to be discovered at the end of that thing. We'll get to that later on. In any case, that's one quantity, the new phase, for the moving frame. That's what the prime means, is we're moving now, look out, here we come. And when you flip that to the inverse cosine, that's the hyperbolic secant, and the flip of the frequency is the tau, that's 4/5. Well, that's an intercept. That measures the intercept. That's the period of the phase wave. It hits the, you know, if you just imagine you're standing still, I got hit here and then I get hit here again. That's the period between hits. Okay? And actually you're getting hit by 2 zeros here. And that's why I always say you've got to have a complete wave inside the unit cells that we work with. Okay? So there is your hit period. Okay? And then it's either 0.8 or 4/5. That's why I like to use fractions to describe things. It's much easier to see what's going on. So this is all 3, 4, 5 triangle stuff here. All right? And that's just showing it more clearly. Okay? There's the flip of this, tau phase. Okay? So there's the two central columns of this thing. The Doppler shifts are on the very end, then the rest of it is made up of similar quantities. Okay? For example, if I'm going to be talking about velocity, I'm going to be taking the ratio of the sinh, which we haven't mentioned yet, and the cosh. Okay? For phase, that's the fast stuff. It's laid over. It's not infinitely fast, it's just really fast, and then faster than light. Okay? So this is 5/3. You can see that. Now this is really important for quantum mechanics because you see the heartbeat part of a quantum wave looked at precisely is never slower than light. It's always faster than light. For it to go infinitely fast is sort of its zero. That's where it likes to be. That's an instanton. It's everywhere in the universe. Oh, wasn't that wonderful? That's what's making quantum mechanics weird. That heartbeat that you can't get at. Because as soon as you go in there with another wave, the groups and the hearts and everything get all mixed up. Okay, talk about group. All right, much more sedate. Okay, here it's only 3/5, but it's got that Lorentz contraction there. 4/5, 0.8. Okay, that's one of the things that's very important for this. That's this guy right here. But we'll get to that later. This one is just giving us that speed, 0.6, 3/5. Okay, the G slope. Okay. Now we're talking about this vector, and now the hyperbolic cosine is the horizontal part of the G, and the hyperbolic sine, 3/4, is that. We'll come back to hyperbolic sine cosine in just a minute. So this guy flips to that. Okay, 3/4 becomes 4/3. There's your intercepts right there. It's much longer period for the group because it goes slow, relatively speaking. Okay. All right. Now, there's some famous name coefficients in this table. I would say this is the second of them. You don't teach this in the sophomore physics. You should. Now you can, because this is so easy. But you have to be careful with this particular thing, because you see, there is quite a difference between 1 1/4 and 1 1/3. Okay? This thing right here, 1.33, okay, the tau of the group, okay? The tau of the group is right here, 1.33, is 4/3. That's really close to this one, which is the kappa of the group, okay? The lambda of the group, that's the flip, okay? But these guys are really close, and so are these guys. This one actually closer, right? So don't get confused between the hyperbolic sine and hyperbolic cosine and the two things that we're going to be talking about that involve a sec. That's the trouble with 3, 4, 5 triangle. They make those really close. They're close to a symmetry. But well, here's what we're really doing. We're taking the group vector, which is cosh and sinh, and that's, now it's right, 5/4 and 3/4, and we're taking those numbers as coefficients of the unit vectors of the original G, which was like this, and the original P, which was like this in the space-time, and like this in the per space-time. Here's the G laid out. Here the P was laid out in space-time. This is per space-time now. Okay, same geometry, just flip those things around the light cone. Okay, anyway, this is the Lorentz transformation. G prime and P prime being added to make with sine and cosh, or cosh and sine, no minus sign, so it's easier than rotation where you'd have a minus sign here and not there. This is what you get, and it's really quite elegant and simple. So this is a Lorentz transform matrix that's made with these two guys. So in addition to being this and this, they are also the coefficients of a transformation. But here we get to look at the famous guys, okay? This is the one that's Einstein's, okay? This is the Einstein time dilation, where you get 25% increase in how sluggish you are on your clocks. You have dilated by 25% here. Clearly, with this number, and there's the old formula that you're used to. These are the old-fashioned notation, which I do not recommend, and I don't really recommend this parameter much either. That has turned off brains for over 100 years, basically. So I put it in there, though, so we make connection. Okay. And if you click on this, you get a table that you can vary the numbers from something besides 3, 4, 5 triangle. But there they are. Those are the two things that sophomore physicists would learn about, right? And he and she both would be completely puzzled. What the hell are you talking about? This is where physics gets a bad reputation. This is bad politics. You're not being clear. You're not answering the question. This is the beginning of answering the question based on waves. Okay, so there's the names of the various effects, and of course, this fellow right here is the past-future asymmetry factor. All right, now we got to do some rushing here. Note that there are animations of these things in action, which are really fun to play with, and also there's this thing, which I'm going to zoom through really fast, but. The question is, what velocity must Bob accelerate so he sees beams with equal frequency? He's seeing a 600 this way and a 300 this way, okay? Now if it had been, let's see if I've got that right. If he had seen a 1200 versus a 300, we know the answer is 3/5 c, 0.6. This is a little slower, but what? This is playing the whole movie backwards. Okay, and what is that frequency when he does get them so they have the same color? Okay, and I say this has a Jeopardy style. This is double Jeopardy. Okay, this is Doppler Jeopardy. Answer by question. The question you ask to answer this is, what is a beam group velocity? You want to catch up with that. That's the classical velocity of the lumps in the waves. It's got a heartbeat that's crazy, but the lumps are very well behaved. And so you try to catch up with them. Okay? And that's easily done. I go omega difference, K difference, but then I know that omega K is related by C, so I put C there. Alright? And then I put 600, 300, 300, 600, that's 600 minus 300, that's 300, that's 600 plus 300, 9, 1/3. 1/3 C. That's slow compared to 3/5 C. But that's what he's got to do. And then, in order to find out what that equal frequency is, it has to be the blue shift of the loci, omega L, and it has to be the red shift, also the red shift of the other one. Okay, so those have to be equal. That gives you this. The blue shift will be the ratio of the two. Okay, and that implies, when you put it back in the original equation, that this frequency is the square root of their product. This is difference mean over arithmetic mean. This is geometrical mean. So the three means are going to play a role in the geometry of everything we do from now on. So what you got here is the product of 6 and 300. That's 18 times, well, it's 180,000, but just think of it as square root of 6 times 3. That's 3 times the square root of 2. That's 4.24. So we're talking about 424 as our terahertz. Okay, a lot less than the 600 terahertz that we were looking at before. Okay, it's going to be red-yellow frequency. Okay, so this is the idea. Arithmetic mean, geometrical mean, and difference mean. Those are the things that play in the interference of the lasers. And here is the diagram that we were talking about before that involved phasors interfering with each other. Here it is in per space, looking at it with the geometry. And this is Thales rectangles and the corners of them giving you the geometrical mean. So what we have here with Alice coming at us with an ultraviolet shift of 4. She's in the 1200 terahertz, and this was this little infrared thing that we're running away from Carla, and that gives us a 300. Okay, so basically it's a redshift of 1, down from 2. This is a redshift of 4, up by a factor of 2 from 2. Okay? Well, you know the answer is going to be 2, right here. That's a geometrical mean that you find after you have struck an arc to make the arithmetic bisect the thing. Where it hits here is the thing. And then right here, of course, is the difference mean. And the line that's there is right on that rectangle that is the baseball diamond with its massively long first base, a very short skilled second, and then back down here to third base, which is the left laser. Cool? Now this leads to a convenient construction of something that's really important.
I need to go.
Okay.
Have a good break.
Yeah, you too. Merry Christmas and all that. Yeah. Okay, so the idea then is that anytime you want to find a point on this amazing hyperbola, and the hyperbola is there because we always had to take the baseball time elongation factor to be the inverse of the shortening, so that the area of the baseball diamond for all possible speeds is the same. That's the way to look at relativistic invariance. And all the points on the baseball diamond have to be on congruent hyperbolas. The pitcher mound does this, the second base does another one that's flatter. Whatever this particular distance down here, halfway to the pitcher's to the home plate, is a sharper hyperbola, and then home plate itself is a degenerate hyperbola. And that is the beginning of quantum mechanics right there. This is MC squared right here. So that's what's coming very shortly here. But that is really important, this particular thing. So what this is telling us, Thales knows how to make a hyperbola real well. All he does is put a compass here, okay, stretch the compass to here, and then strike an arc till it's right over where he punched, and that'll be a hyperbole point waiting there for him. That's kind of neat, okay? That's the real ruler and compass construction of the most important part of the quantum mechanical dispersion curve of this box of light, which has to mirror the dispersion curve for every other piece of quantum matter. Okay. There's some more pictures of it, and there's also animations and things that you can do. This one would give a picture like that that shows the whole Minkowski rhombus for two cells sitting there tangent to the new pitcher's mount point. And then the group is doing a similar thing on a hyperbola that's over here. So all those hyperbola functions are getting to show themselves rather clearly. Now, since we don't have much time, I want to point out there's a whole other way to look at relativity. This guy whose name rhymes with Einstein is Epstein, Lewis Carroll Epstein. He's trying to take credit for the British author of Alice in Wonderland, and also have Einstein along for the ride, I guess. But he's an interesting guy, sort of, but very narrow. I was amazed how narrow he was. He just didn't really see the connection between these things. But the basic idea of the stellar aberration angle is really crucial. That's the transverse way to measure speed. This very first picture here shows. I've liked it coming straight down across my line instead of along my line. I don't look at the Doppler shift first. At first you don't have any Doppler shift. That's the second order as you go forward, and the light turns and gets in front of you by an angle we call sigma. So as I say here, I use the notation sigma as a flipped out rho, but the rho is the longitudinal way to measure speed. This is the transverse way to do it, and it involves ordinary sines and cosines, not hyperbolic cosines and sines. Well, long before that was realized, he had written a book that took advantage of that. And so basically what he does is he takes the hyperbolic form for the relativistic, and this is just 1 minus v squared over c squared, with a ct squared taken to make this thing a ratio of the two. But that is the normal relativistic expression of proper time. He's going to turn that around. He's going to make it into a circular form. He just flips it. So he has c tau squared plus x prime squared is equal to ct prime, the coordinate time. That's this. So from then on, he's dealing with circular functions. Lorentz contraction becomes a cosine projection. Time dilation becomes a secant projection. Okay, that's very clever. Okay, and this is the way he taught relativity at the City College of San Francisco, which was the feeder school for physics people that couldn't get into Berkeley first time through. They go there and take some really good courses in physics, and then they get into Berkeley. So that kind of what was going on at the time this book was published. But no one would accept it to publish. He had to self-publish, and unfortunately his father owned a print shop. So I recommend buying the book. That's, just Google it and you'll get it. It's about 15 bucks. Brand new. Probably get them for less than that.
Someone who beat us to the mark. All of Professor Harter's stuff's out there available now.
Yeah, we're a little cheaper. Our stuff's all free. But that's the way it goes. Sometimes you can't give it away. Anyway, this is the thing that shows how you get the stellar aberration angle. It's the one that goes essentially makes a little thing we call Occam's sword. I'm going to real quick show you that. There's a little sword that comes here, and these points are all important as you zigzag your way down. That's geometrical ratio, right? This has geometrical sequence that's happening there. It has a kosher depending on which direction you're going. So this sort is really powerful if you're going to study microwaves, okay, in a cavity, microwave guide, right? Here's an example of a simulation of it when I have the light quite well directed, so the rays are pretty much down the cavity. Now that's actually a terrible angle to have, but here's the group velocity. You can see it's slower than the phase velocity. You can see here's an excerpt of that sword geometry. Okay. Now I'm going to quickly stop this so I don't use up my laser. There. Go back, and here is really close to the cutoff of the thing. Now you can see the group velocity, which is 0.5 c, is really a lot slower than the 2 phase velocity. Okay, it gets left behind. Okay, while we're looking at that, I'm going to move this guy ahead as well for other purposes. We'll have just a minute here. So let me go back on this one and get the thing up to this region of discussion. This structure, okay, is what is letting us have these velocities. And I'll go ahead and just put it on this one. There's a case where you're got a really big oakum sword, and that's because we're talking about a phase velocity. It's really fast, but the group velocity is not so great. Okay. Then this one down here is kind of the opposite. Okay. In this case, the group velocity is really slow. Phase velocity ripping along. Inverse to that, and they're all marked there on the thing. There's the two of them together. Okay. So the signal, the actual signal, that's what group velocity is. The classical signal, okay, is going that fast in a waveguide that is really close to cutoff, close to the bottom of the hyperbola, which is we're going to see the mass shell of a quantum interpretation of quantum matter. Okay, let's switch over right now to the other this final part, which is, we'll just do a little bit of this. I just want you to see how this goes. And this makes a pretty crazy claim. And that claim is that we're going to derive what are considered axioms. We're going to derive some axioms. Planck's axiom. Okay. De Broglie axiom. They're separated by 21 years in the history of quantum mechanical development. But Einstein sort of sidestepped both issues in 1905 when he talked about the photoelectric effect. And won the Nobel Prize eventually for that. And the relativity was so crazy to everybody that was in Europe in the Germanic side of things. Plus, they called it Jewish physics. Right? They didn't like Jews. That's a shame. So things got held up. That's what really happened there. So let's go ahead and play this and get a feeling for what it is that it means to derive quantum mechanics. First step, okay, is to look at these two. We know the phase is the heartbeat. Let's look also at the kappa, not just the frequency of the phase, but also the kappa of the phase. They're the real key to how things work in the microscopic universe. Okay. So we're talking about a thing that is a hyperbolic cosine and something that's a hyperbolic sine. Okay. Now that's approximately 1/2 rho squared times this base coefficient. B stands for the bottom of the hyperbola. in our diagrams also, a base. Okay. And then this one right here is just B rho, hyperbolic sine, like the ordinary sine is just the independent variable. Straight away. Okay, but this is all for you way, way, way later. None of this going around the Earth in three times in a second. We're talking about 10 miles an hour, 3 miles an hour. We're walking speed, Newtonian speed. So Koch and Cinch approximations are what gets us started. Okay. Now remember what B was also. It's the frequency that Alice lays in 600 terahertz for us. Okay, and then it goes with the C kappa as well. The kappa alpha is B over C. So this would be the second term, rho squared, because rho is hyperbolic tangent, also just rho when you're going slowly. Okay? So we can just put the U over C, that's the old-fashioned parameter beta of relativity. I'll stick that in there now. And people that are used to that utter sigh of relief, say, oh, I recognize that. But mainly it's U that we're going to be interested in. So here's what the new phase is. Okay, this thing right here, when we've got this all stuck in there, okay, rho squared, and you got a C squared in the denominator there. Okay. And then we go and, while we're at it, for U less than C, we see what the kappa phase comes out to be. Well, that's pretty easy. After we get done putting this in there, we see the kappa phase, because it used to have a C in front of it. Now we've got the C in the denominator along with the B over C. So you get two coefficients here of velocity and velocity squared that are the same. So that says, my gosh, this resembles 1/2 mu squared, except for this constant, I don't know what that damn thing is. But the same m here. This is mu. These are our quantities are resembling the formula for Newton's kinetic energy and momentum. So this is the connection. This is the doorway to this. And notice we're going with very elementary things. The usual connections are done with all of the Hamilton-Jacobi stuff, which is really hard to teach to sophomores. Anyway, it's clear that we have to rescale this thing. We have to rescale by h. Okay, well, h. You already know what that h is. It's Planck's constant. Okay, we got to rescale this sucker. Okay, in order to make the units correct for our new phase and our kappa. Okay, and that does it. And that's explained in some detail there. So we attach a scale factor to match the units. Okay, that's all we're doing. So after we write that out, okay, we notice that this thing, the kappa phase becomes that hb over c squared, whereas that's the m. That's fine. That is giving us a mass times velocity. But what's also notable here is that the hb is just mc squared. See, right here, hb is mc squared. So the Planck's constants times the base, that's mc squared. That's why I pointed at the bottom of the hyperbola and said that's mc squared. M being the mass of this box of light. That's crazy, right? The idea that the light has mass, you see? But at this point, most people would look at this and say, my gosh, is that really going to work? I mean, it sure looks kind of nice. Looks like a lucky coincidence or a cheap trick. Okay. But we're not done yet. Remember, we took approximations. Let's try the exact new phase. Okay? New phase. All right. Hyperbolic cosine. Kappa. Sine. Let's do this one. We'll do this one for a few slides, and then we'll work on the other one. There's 21 years between doing that and that. Okay? We take 21 seconds. So, here's the hyperbolic cosine times hb, which is mc squared. And what's the hyperbolic cosine in old-fashioned language? In old-fashioned language, it's this. So you have, except for this constant, and the constant is the same letter Planck used, so it's truly the constant. This is the Planck axiom and the Einstein relation for energy. Bingo, you got it. It just comes right out of this table right here. It's new phase. Okay? Now we do need to replace it. What we got was the n = 1 result for Planck. Planck knew that he had some sort of thing that he had to get a ladder of really quantum oscillator states for the electromagnetic field. And there's an H and N nu, okay? And this made him really worried, because what he was showing was that with his way of looking at things, the energy is linear in the frequency, and that's screwball bad. He thought he should go home and shoot himself. His career was over. How can you be so stupid as to have something that has an energy not equal to omega squared? Well, stupid like Fox, right? Okay. There's two frequencies here. One's the count rate, when these really complicated combinations of phase and group connect with some other complicated thing and make a count. And that occurs at a certain rate, which is not a smooth rate. It's a probabilistic rate. But the two frequencies here, n per second and frequency is n per second. So he has it right. It is frequency squared, but just weird frequencies. Okay? And it also motivates the idea of why do you have to normalize things? And where we're normalizing, we're getting n, but most of the time you take n = 1. That's quantum mechanics with n = 1 for this field that we're talking about here, this electric field that's being imitated. So as I say, big worry, oscillator energy, not nu squared. Well, it is, dirty secret. E is also a frequency, n is also a frequency, nu phase is also a frequency. This really comes down to this, and the epsilon takes care of the units. So it is quadratic in a frequency that is related to things. So there's our final formula. That's really what we're talking about as far as energy goes and making some sense out of it. But then there's something else to do here. The kappa phase, okay, we need to stick that value in. We've got to stick that value in to this formula right here, okay? And when we do that, we get de Broglie's relation. That's this guy right here, okay? That 1 over b minus 2 squared minus 1 is just the square root of 1 minus with the beta up here. That's the old-fashioned notation. So there's your momentum. As I say, it took many years to go from Planck. Planck was 1900, and there's 1905, where Einstein kind of gets this, but doesn't recognize it at first. So that's the basic derivation of the quantum matter. That's the dispersion function, energy versus momentum. So what is energy? Inverse time, with a funny factor to make it so that you're used to it, and called joule after joule, right? You don't need it. It's inverse time. And this is inverse space. So that's the really cool thing. Now the rest of this, there's the table. The rest of this is just to show that this thing right here becomes the Lagrangian, this thing the Hamiltonian, this thing right here, the past-future asymmetry, turns into momentum. That's what momentum really is. It's this thing happening. And the Lagrangian is this thing, the phase, doing its heartbeat. And the Hamiltonian is an internal frequency. If you can ride with the object, then that's the frequency you see. So these are really two sides of the same thing. And then the de Broglie wavelength is just the inverse of the momentum. So it's really gets to be a very tight piece of logical geometry that is really quite weird. Now the rest of this is just, what's the matter with mass? There's the elephant in the room, okay? literally. It says, I matter. I mean, right now we're going through this. Black lives matter. There are all kinds of things that matter now that didn't matter before for some reason. This is one of them. This is one of them for physics. Okay? Let's use our formulas to figure out. First of all, there's this rest nest. That's completely new. That wasn't attached to energy before. Now we know we have to attach it to get the right enormous phase frequency. It's just enormous. It's a terrific heartbeat. Even for an electron, it's 10 to the 24th hertz. For just one electron. Then this momentum expression, also important. And then the velocity expression. So what I'm doing here is I'm taking Galileo's mass, I'm trying to find Galileo's mass somewhere in this thing as a ratio of P equal mu and u. Well, that's mass, isn't it? But I'm going to use the modern versions of u and the modern versions of P that we just derived. Okay, that's what you get. Sinh over tan. What the hell is that? Is that any kind of mass? Yes, it is. It's this one. That is what people call momentum mass. It was just the coefficient sitting in front of de Broglie's relation. So that's not surprising. But here coming is one. Limiting cases. And notice that as you go really fast, this one blows up exponentially. And that's the characteristic of all of this relativistic stuff. You push it, and it blows up exponentially. All of those things are made of exponentials. The e to the minus rho just go away, and the e to the plus rho is the thing that's going to live, and it's going to blow up in your face. So you've got to expect that. That's what mass is doing. But it can do it even faster if you talk about force or acceleration. Here's the effective mass. That's the name that should be used. It has to do with acceleration. Okay? So now, what we're doing is we're defined by the ratio of the change in momentum to the change in velocity. Okay? However it changes. And we know how it changes because we're going to put the modern values in there. So it's cosh over sheik squared. Well, that's cosh cubed. Right? This is just inverse cosh, but it's an inverse, so you get two more coshes attached to this thing. That's the effective mass. That's one way to state it. But another one that's really spooky is this one. Just use the basic group derivative relation and find out that you're dealing with a second derivative of frequency with respect to k. This is the group velocity. We haven't really mentioned that that is the correct relation, but it is. It's one of the more amazing things about this geometry. But in any case, here's where you end up. And this time, if I'm going to use a k instead of a kappa, I got an h bar. That's h over 2 pi. So this is an exact formula for all kinds of things in band theory. This is the way you do it. You look at the curvature of omega versus k to determine effective mass. So this is a very general wave formula. And it is purely quantum mechanical because it has that scale factor. So you look up the hyperbola, you start out with, this is the smallest circle, the minimum radius of curvature. That means maximum curvature right there, and then the radius of curvature blows up. The radius of curvature is proportional effective mass. So the effective mass gets bigger as you go out there, just like the momentum mass, except it does it with a cube. Okay? Photon has all three of them, depending on what you're doing with the photon. Okay? Now, here's where you do the stuff that we did in this class. You just say that the Lagrange is the derivative with respect to time of the phase. The phase is what we started with, kx minus omega t. Now, what's interesting about a phase, as I said, it's invariant. So the space-time is filled with points of given phase, but every observer sees that point with the same reading on the clock, same phase reading. That's the gauge invariance, really deep concept. But once you've taken it, I'm going to just simply let the phase with the scale factor, just like I put an h bar in front of omega, I'm going to put it in front of this derivative of frequency, or of phase. So that's the de Broglie momentum relation and the Planck energy relation being stuck in the k and the omega. So what you're ending up with is Poincaré's and Legendre's transformation, but right now it's just to energy, this relativistic energy. But we have a name for that energy. That is Hamiltonian. And this was just P times velocity. So there is the Legendre transformation right there, just given to us. Now we looked at this a little bit in the elementary unit, unit 1, but it's, it is really, this is the doorway to understanding a lot more, because now we know that we need to go get the Hamiltonian Lagrangian for some complicated thing like a microwave cavity plus guide and all sorts of complicated things that would happen there. But this is just, remember, just the two plane waves colliding in a box that we're talking about here. Okay. So here it is, and I put those values in, the modern values for these things, and come up here with a Lagrangian that is simply the sec of rho with a minus sign. Now what's that minus sign? That's really crazy. And then the Hamiltonian, okay, we pull that one up. That's the old-fashioned notation for it. That's our rho notation for it, okay? And these are all based on these relations that are in that table that we looked at, okay? So here is the hyperbolic function that the Hamiltonian is. The hyperbola is the Hamiltonian, okay? And then this is the secant of sigma. This is the transverse way of looking at it with a stellar angle, and that's useful. And if you define the action like we have here, you've got that too. So that's the basic idea. I'm going to stop here. It's a little over an hour, but this is the diagram that has all of those Kaj. It's Kaj right there. That's Hamiltonian. Lagrangian is the sec. It's the inverse with a minus sign. So this is minus a Lagrangian here. The real Lagrangian is down here. That's the Lagrangian function right there. It's a circle. Exactly. Relativistically, quantum mechanically. This circle has the same curvature as the hyperbola. You see them kissing each other right there. The top of the circle kissing of the Lagrangian function. This is minus the Lagrangian to that circle. And remember, Lagrangian's got to be a function of velocity. That's the group velocity right there. Group velocity. That's a hyperbolic tangent that we worked out shortly after we made the graphs of space and time. It's also the sine of sigma. Okay? Here's sine, there's cosine. Sine and cosine. The sigma is the Lagrangian's polar angle. That's the stellar aberration angle going right up there, pointing at the star apparent position at this speed if it had been directly overhead before you got moving this fast. Well, what more can I say? Also, I mentioned the fact that the derivative of the hyperbola, okay, the derivative of the Hamiltonian, well, it turns out to be the velocity. That is, it turns out to be hyperbolic tangent, or sine, okay? And that comes back here to intercept at exactly the height of the Lagrangian, minus Lagrangian, okay? And then you go over to the Lagrangian and do a tangent there, the derivative of it with respect to its independent variable. Well, that is this guy right here, the momentum, hyperbolic sine, you see. So you go back on that tangent right to here and you hit where the Hamiltonian is. Isn't that elegant? Now you take, this is where it helps classical mechanics, because those functions are just, where did you get those things? Right? You manipulate some stuff around, but this is physically where you get it. Just for a box of light. And of course, this is what, and TC has agreed that we probably ought to do some stuff in the bottom
They're
here.
there.
Let's give it a try.
Some of it's showing.
And maybe I will have to empty the cache, but we'll see.
You got it.
It looks like it's there. Yep. there it is, nicely tangent to the positive Lagrangian. And as you go like this and start working your way out, making a huge occam sword, you see the Lagrangian is approaching 0, and the group velocity is approaching c. So you can see why particle physicists use Lagrangian, because all of their functions are down in probably 1 pixel. The high energy physicists work inside 1 pixel, and where my finger is pointing. And all of the functions that they work with are finite. Whereas the Hamiltonian is gone bye-bye, right? Because momentum has no limit. And what we work with, you see in this laboratory, is essentially we work inside 1 pixel right there. And we use Hamiltonians. Lagrangians, who wants to work with a Lagrangian, when we can work with a Hamiltonian. But you see the Lagrangian and Hamiltonian have similar magnitudes, right? So a lot of things you can learn from just playing with this thing, watching all of these. And as we put more geometry on it, I think we're going to begin to understand how it is that you make matter that you can keep by putting 2 beams together of the right frequency. That's called the pair pair creation, basically. But the idea is that you have 2 waves there, one electron and a positron, doing a little dance around each other, and if you're lucky you can hack something to make the electron go this way and the positron go this way, and they can't get back together again easily. Just as we don't really understand all of the wonderful things that happened when 2 black holes that were orbiting collapsed and blasted the universe with as much energy as coming out of all the stars we can see. That's an incredible thing that happened there, and you probably wouldn't want to be anywhere near it. But so also, we do not understand what happens to a collapse of positronium. Positronium has got this light, orbiting. I mean, it's an electron and positron orbiting, but that's 2 pieces of wave geometry orbiting, right? And if it collapses, the light goes out. We understand that light. We understand 2 plane waves, or nearly plane waves, emanating from a collapse of positronium. But what happened in that collapse? What's the geometry of that collapse? And what's the geometry that allows you to have it break apart in another way where electron and positron come out instead of 2 pieces of light? Now, black hole's not going to do that. Black hole's not reversible. This is. Time symmetry does not exist for monsters. But for little guys, they can have it, right? It works very well for little guys. So there are lots of food for thought by having this picture to stare at every day. Or pictures like it. We're going to be trying to go to higher dimensions. I mean, 2 more dimensions here. We essentially already have it with the stellar. That's the stellar angle right there. So we can kind of work the so this is 2 plus 1 dimensions. We need really to handle that 3rd one, x, y, and z.
You could see the 1 sort of surface of revolution. You can pick up that extra dimension just by revolving it.
Yeah, you can have a kx and a ky, but kz has been, the space for it has been taken. So you have to play some games with that. Yeah. So I hope you're excited about this at some point. And you see, it is really the end of the mechanics course, right? And we're going to start with this in the atomic and molecular and take a lot more time on it. So if you're interested in doing that, sign up. So far we have nobody signing up for it.
I have other classes that I might actually take an astrobiology class to talk to advisor today.
Again, it will be a small class.